Hello and welcome back to Aerospace and Mechanical Lab 1. Today we are going to discuss the tensile test. The idea is we are going to review the basics of a stress and a strain today, and we will talk about deformations and how different types of deformations in metals specifically. We will move on to stress strain care for metals, and we will discuss the stress strain care for composite, and we will talk about the test itself. This should be lab 4. So lab 4 tensile test. Okay. When we apply an external load to material, based on the type of load that you are applying, the material is going to deform, is going to react to the load. For example, if you apply a tensile load like this, we will see an extension in the material, in the direction of the load. We also are going to see a shrinkage in the transverse direction, in the other direction. When you apply a compressive load, as you can see, we will see compression in the material and expansion in the transverse direction. When you apply shear load, we can see an angular deformation. And the same is true for tension. We have already discussed torsion in our lab 2. We have seen how torsion essentially affects the material. Essentially, we have investigated the torsion of the material, but all of our investigation so far has been in the elastic region. So we want to move on to the plastic region in this test as well. The idea is in the elastic region, the deformation of the material, essentially this change in length, delta L, is related to the applied load through the Hooke's law. So essentially, load is equal to the spring constant multiplied by delta L. When you bring this in into materials and applied load, this will become a stress is equal to modulus of elasticity multiplied by a strain. This is only true for the elastic region, right? And a strain is defined as a dimensionless parameter that can be calculated by dividing the change in length of the material by the original length. A stress can also be defined as applied load divided by the area, the cross-sectional area, this area specifically, wherever you are applying the load for the material. You want to keep in mind that as we applied load, as we saw in the previous slide, as you are applying the load, your area is going to change, especially in the plastic region. So when we use the initial area as our stress calculation value for area, we are calculating the engineering stress, which is the case in our lab, right? But when you are calculating when you keep track of the area and you use the real-time area for your stress calculation, you are calculating through a stress. And again, based on the Hooke's law, a stress is equal to E modulus of elasticity, or Young's modulus, multiplied by the strain. One of the things that is very beneficial in material science to have is the sigma epsilon or stress strain curve. In the stress strain curve for a material, we have a linear region, which essentially works based on the principles of Hooke's law. Then we get to point A here, where the plastic deformation happens. We call this point the yield point. Actually call this point specifically, which is 0.2% away from point A, the yield point. This is where the material has yielded to the load and a plastic deformation begins. Essentially, the idea is when you have plastic deformation, your material is not going to go back to its original form, which is not the case during the elastic deformation. As you're going to see in the lab, the elastic part for aluminum specifically that we are going to test in this lab is very, very small. So most of the deformation is the plastic deformation. And then the stress is going to go up at a different rate compared to the elastic rate. At some point, the stress is going to be a maximum, right, which we call the ultimate strain. And then the stress is going to drop on the stress strain curve, and at point E, we are going to see a fracture where there is a break, the material actually breaks, right? For different types of material, for different sizes of material, the stress strain curve is going to change, right? And based on this, we categorize materials. Like you can have a stronger material, you can have a stiffer material based on how this strain stress curve is looks actually. So when it comes to metals, we have three different types of metals, and they behave differently to an applied load. First type of metal that we want to talk about are the very ductile metals, soft metals especially. These are soft metals at room temperature. These ductile metals are very plastic. They can have a huge plastic region. Then we'll move on to moderately ductile material, which is the most typical form of metals, in which you have a plastic region and an elastic region. Plastic region is not as big as it is for the very ductile material. And eventually we have brittle material like ceramics or cold metals, where the plastic region is pretty small. So essentially the material only behaves elastically. And for these different types of material, we have different types of fractures, right? For very ductile material, you're going to see a lot of necking, right? This is called necking, a lot of necking. And then at one point, material is going to break after a very lengthy elastic region. For a moderately ductile material, we are going to see some necking, but then we are going to see a somewhat of a clean break after a moderately sized elastic region. For brittle material, a plastic region is basically non-existent, and there is only a total fracture when we reach to the height of the elastic region. You can see there is a clean break here. This is true for the soft material. So the material we have in the lab, we are going to have a composite dog bone sample, which are the samples we use for the tensile test, that usually break very cleanly like this. They don't really have a huge plastic region. We have metals, two types of metals that are moderately ductile, and then we have plastics that should be a little more ductile compared to the metal and the composite. Okay, as I just brought up, we are going to test these, do the tensile test on a composite, on a carbon fiber composite dog bone sample as well. So this essentially means that we need to have a better understanding of what composites are. So composites are anisotropic sheets. Essentially, what an anisotropic sheet is, or material is, it is a material that has different properties in different directions, right? Which essentially means that the Young's modulus you calculate for the x direction is going to be different from the Young modulus you calculate for the y direction. And the reason is that we have fiber placement and epoxy, and based on how you actually create the composite panel, based on how you place your fiber, your modulus of elasticity is going to differ. In lab 2, when you take lab 2, we are going to have a lab in which we actually create a composite plate, and over there you are going to have a better understanding of what all of these mean. Okay, so another example, this is your typical isotropic material, composite material. The fibers can be laid out in this direction and then connected to each other using proxy, or can have a woven pattern. This essentially means that these two materials, although both of them are composites, but they are going to behave differently compared to each other. And this one material, as you can see, in this direction, it is going to be easier for it to break, of course. It is visually evident to us, right? But compared to this direction. And we can actually see this in the numbers here. Okay, another type of failure we see in composites, other than fracture, essentially total material rupture, is called delamination. Delamination is essentially happens when you have a material that is made up of different layers, which is true for composites. So for composite, you actually put a couple of fibers on top of each other, add resin to it, and then let it cure, right? Which means that the layers can separate from each other. So, and we are testing a composite panel. We might be able to see delamination based on the composite. Delamination doesn't always happen, sometimes happens. So if you see delamination, make sure to take a picture of it and include it in your lab reports. Okay, for the lab itself, you will be given 4 to 5 samples, and the idea is all of the results needs to be shared with all groups. So you don't really need to be worried about it. And about the results as well, your TA is going to take care of it. And we have the aluminum samples. We'll be giving you the aluminum samples and 2 different plastic and a composite. You are going to be testing all of those. The idea is we are hoping for each student to do the test themselves. So this test might take a long time because we only have one tester. And you also need to keep in mind the lab itself is located in room C004. Please let me know if you have any questions and have a good day.